Greetings, AP Chemistry students. Today we're going to transition into the last part of Unit 9, which is electrochemistry. And I hope to finish this up next Tuesday and Wednesday. And then Thursday and Friday of next week, we'll look over some of the stuff from the AP exam because they're supposed to release your results to me. And so we'll have a little Google Meet then to talk about all that good stuff. But electrochemistry is one of the most important aspects of chemistry to your day-to-day lives because things like cell phones and laptops and all sorts of other things that you depend on as part of modern life would not be possible without electrochemistry. But electrochemistry is the study of redox reactions that occur within electrochemical cells. If y'all remember redox, that's oxidation reduction. Oxidation is losing electrons, reduction is gaining electrons. And electrochemical cells are devices that separate those parts so that the electrons can move. And a device called a galvanic cell generates an electrical current. And I have two examples of galvanic cells for you. I have this one right here. This one right here is a D cell. And then I have this one right here. This is a size AAA cell. These are commonly called alkaline batteries, but this is technically not a battery. This is a cell. This, on the other hand, is a battery, because if you were to actually open this up, you would find inside of this 6 tiny little cells connected inside of it, because each one of these cells generates 1.5 volts of electrical potential, which we'll talk about. This generates 9 volts, and if you multiply 1.5 by 6, you get 9, and that's how you get the 9 volts. Is there's packaged inside of this little rectangular prism are 6 of these, of a smaller version of those little cells. So that's a little technical difference. Now, there's also what's called an electrolytic cell, and these are ones they don't generate electricity. These are ones that you apply electricity to and a reaction happens. A rechargeable battery, when it's being recharged, is an electrolytic cell, but there's a lot of other cool applications of these as well. But galvanic cells are devices that convert chemical energy into electrical energy. And there's a redox reaction that takes place, and the substance that's being oxidized transfers its electrons to the substance being reduced. And if you look at how this actually works, the oxidation part, electrons are being lost out of the negative end of this cell, because electrons are negative, and they flow through. And then on the other side, the positive end is connected to the reduction side where the electrons are being gained. And essentially, there are half reactions that are separated by a salt bridge. So you have oxidation taking place in one part, reduction in the other, and they're separated by this device called a salt bridge that will separate the reactions but allow electrical charge to flow. And some terminology that's used with these: the anode is where oxidation occurs, and the cathode is where reduction occurs. And on a galvanic cell, the anode is the negative side of the cell, and the cathode is the positive side. Now, cell potential is also known as the electromotive force, or EMF, which is abbreviated with a capital E. That is the driving force, or what actually pushes the electrons along. And it's measured in volts. So I already mentioned this provides 1.5 volts. This provides 9 volts. The battery in your cell phone provides around 4.2 volts. And technically that's a cell, not a battery in your cell phone. The battery that's in an automobile provides 12 volts. But a volt is a joule of work per coulomb of charge transferred. And a coulomb of charge is essentially the amount of charge contained on a specific number of electrons. Now, all thermodynamically favorable galvanic cells, in other words, these things, they produce a voltage, a reaction happens, they have a positive cell potential, meaning that their change in Gibbs free energy is negative and their equilibrium constant is greater than 1. So all three of those things play together. And as you might guess, there's a relationship between these things. Specifically, the change in Gibbs free energy equals negative NFE, where E is your cell potential under standard conditions. This is Gibbs free energy under standard conditions. There's a negative sign there. But then F is Faraday's constant. And Faraday's constant is 96,485. That's on your chemistry reference tables. That means there are 96,485 coulombs of charge for every mole of electrons. A coulomb is a unit that's used to measure electrical charge. And N is how many moles of electrons are transferred in the reaction. So you would have to actually analyze the reaction in order to figure out how many moles of electrons are transferred. Right. So that's kind of a introduction to this. In our next lesson, which we're going to do on Tuesday, we're going to look at how this actually happens inside it. We're going to look at what's actually happening in here. We'll analyze this a little more. Then Wednesday, we'll talk about electrolytic cells, which are the opposite of that.